So in this section, what we'll be looking at is the derivative of exponential functions where the base is not e. Remember, we did the derivative of with respect to x of e to the x equals e to the x in the last section. Now we're going to look at what happens when this is not e but some other number. For example, you could put in the derivative with respect to x of 2 to the x, and this would be just 2 to the x times the natural log of 2. So it's the same thing as before. The only thing that changes is that whenever you have an exponential that the base is not e, then you change and you multiply everything times the natural log of the base. And when you're doing a logarithm, same deal, you get 1 over x as before, but then you have to multiply times the natural log of the base. So it's very similar. We just have to multiply whenever it's an exponential times the natural log of the base, or divide if we're doing a logarithm. So let's do a few examples just to make sure everything makes sense. Here, for example, you copy your exponential. I'm putting it out here so I can multiply times the natural log of the base, and that gives you your derivative. So same deal, you just pay with the natural log. Here again, you do the same thing. And what is it? Well, I'm gonna copy the exponential or the whole function. Then by chain rule, I still have to multiply times the derivative of the exponent, so 2x minus 2. And then, because I'm not taking the derivative of e to something but 5 to something, I pay with the natural log of 5. So you do the same thing as before, that is, copy the exponential, multiply times the derivative of the exponent, and you add one extra term, which is basically what you pay for changing your bases. So that's basically how you calculate these derivatives. Now for the logarithm, we have the same. The derivative of the logarithm is 1 over x, but remember that was for the natural log, so we pay with the natural log of the base, in this case in the denominator. What if you don't have just x but another function inside? Same deal as we did before, in the sense that you do derivative of the inside over the inside. So 4x cubed minus 1 over the inside. But since it's not the natural log, but the log base 9, you pay with natural log of 9 in the denominator. So whenever it's a logarithm, the natural log of the base goes to the denominator, and when it's an exponential, goes to it multiplies it. So that's that. And why do we care about these things? Is because we're going to be looking at annuities. And annuities, what is an annuity? Well, it's a payment you make constantly over a period of time. So for example, you could do semi-annual payments to your retirement account. You could make monthly payments to your retirement account, annual, or you could just have a savings account that gives you a fixed interest rate. The one assumption we're making is that you do have a fixed interest rate or annual return, which in the case of investments is not always the case. But if you have an account that gives you that kind of situation, then you can calculate the amount that you're going to have in that annuity given a number of years t, and is given by this expression where p is the payment you're making, n is the number of times you pay for that annuity, and the number of times it is compounded. So we're going to assume that those two are the same, and r is your annual rate of return or annual interest rate, and this is going to be the expression we have. So for example, if you would save $100 a month and put it into an account that gives you a 3% annual rate, and we're going to assume it's compounded monthly, then let's find a function that describes our annuity. Well, we just copy our function here, which is p, the payment is 100, times Then I have this expression 1 plus r over n. R is a 3%, so you put it 0.03. Annual, so 12. Monthly, sorry, so 12. To the power of nt, so 12t, minus 1, and all over r over n, so 0.03 over 12. But this looks way more complicated than it really should, so let's calculate, for example, this, and let's write what it is. So we get 100 times, when you calculate this, it's going to give you 0.0025. So this becomes 1, because you're adding 1, 0.0025 12t minus 1, and all of it is divided by that same 0.00025. This is the same as dividing by 0.0025 is the same as multiplying times its reciprocal. And its reciprocal is just 400, so this becomes 400 times 100, so you get 4 zeros, and that multiplied times 1.0025 to 12t minus 1. And that is our expression. Looks a lot nicer. So if you were interested in calculating our annuity, or the value of our annuity after 10 years, you would just plug in 10 and would be 40,000 times 1.0025 to the power of 120 times 12 times 10, 120. I'm already calculating it, minus 1, and let's calculate what that gives us. And it gives us $13,974. So what about the rate of change? What would the rate of change tell us about this? Well, it would tell us how is the money or the amount in this account growing per year if I would evaluate it at times equals 10, would be at the 10th year. So that would approximately tell you how much money you will have, or how much money will you make between the year 10 and 11. So that would tell you how much is the approximate how much is the account growing at that point. So let's calculate it here. So the derivative of of t would be, well, copy this constant, and you have to multiply times the derivative of this expression. Well, this expression is just one of the form a to the u, or a to a function of x, so we have to take the derivative using the formulas we did before. So remember, what do? Well, you copy the exponential, multiply times the derivative of the exponent, which is just 12, and lastly, since this is not an exponent, not e, but 1.0025, you multiply times the natural log of 1.0025. And then minus the derivative of 1, which is 0, so that is all you have. So let's calculate what all these numbers multiply to, and let's write it approximately equal to, if you want, and let me calculate that. So when I multiply the 40,000 times 12 times the natural log of 1.0025, I get 1198.5, and I still have to multiply times this. So if I want to find out how is my annuity changing at year 10, I'll just evaluate it here, and that would be 1.0025 to the power of 120, which is approximately equal to So it's approximately 1,600 with 17 and 20 cents. So you can see that if you're putting $100 every month, if you had no interest, you'd be just, your account would increase by 1,200 a year. But since you have some interest rate, that changes to $1,617 with 20 cents. So you have roughly $417 that you're making off of interest at that year. And that is just because of the compounding effect of this account. Alright, so that's that for this example. I'll leave it at that, and if you guys have any questions, please put in the comments or just attend the conference this week.